When we deploy an application to US-East-1, we often treat the cloud as a single frictionless point in space. Our dashboards show green check marks and low millisecond averages, giving us a false sense of security. But the label US-East-1 is actually an abstraction that hides a massive geographic footprint spanning hundreds of square miles across Northern Virginia. It isn't a single building. It is a sprawling network of data centers, fiber optic cables, and complex routing tables. Every time your application makes a request, it isn't just going to the cloud. It is traveling through physical glass fibers, hitting routers, and contending with the laws of physics. Understanding this friction is the difference between a snappy user interface and a sluggish experience that drives users away. Today, we're looking past the marketing labels to see the real cost of distance. To understand why your requests take time, we have to talk about physics. Light travels at roughly 300,000 kilometers per second in a vacuum. However, data doesn't travel in a vacuum. It travels through fiber optic glass. The refractive index of glass slows light down by about 30%. This means your speed of light in fiber is actually closer to 200,000 kilometers per second. While that sounds fast, it creates a hard floor for latency. If your server is in Virginia and your user is in California, the round-trip distance is roughly 8,000 kilometers. Even in a perfect world with a straight fiber line and no routers, you are looking at a minimum physical floor of 40 milliseconds. No amount of software optimization can beat this constraint. It is a fundamental law of our universe that every centimeter of glass adds nanoseconds to your response time. Physical distance is only half the story. The internet is built on protocols that require conversation. A single HTTPS request isn't one trip, it's a sequence. First, there is the TCP handshake, a hello back, and an acknowledge. That's 1.5 round trips before a single byte of data is sent. Then comes TLS for security, adding more round trips for certificate exchange and key negotiation. If your base physical latency is 40 milliseconds, a new connection might take 120 to 160 milliseconds just to establish the pipe. This is why US-East-1 feels slow when you aren't physically nearby. It's not just one lie about distance, it's the multiplication of that distance across every step of the connection process. Every handshake is a tax paid in milliseconds.
Once your request finally reaches the Virginia border, it enters the availability zone maze. A single region like US-East-1 consists of multiple isolated locations called availability zones. Your request might hit a load balancer in Zone A, which then routes it to an application server in Zone B, which then queries a database in Zone C. Each of these internal hops happens over high-speed local networking, but they aren't zero cost. Under high load, or during network congestion within the data center, these internal millisecond increments start to stack up. This is the long tail of latency, the P99 spikes that frustrate your most active users. When the cloud provider says single-digit millisecond latency, they usually mean between two racks in the same room, not across the complex orchestration of your modern microservices architecture.
So how do we stop the US-East-1 live from ruining our performance? We stop relying on a single geographic center. The solution is moving compute and data to the edge. Instead of making a user in Tokyo travel 11,000 kilometers to Virginia, we deploy lightweight functions and distributed caches in local points of presence. By terminating the TCP and TLS handshakes locally, we slash that initial 160 millisecond tax down to nearly zero. The data still has to travel eventually, but the user feels the response instantly. The cloud isn't a place you go to, it's a fabric that should exist wherever your users are. Don't let a single region label dictate your user experience. Go global, go local, and stop the lie.